Hi everybody, welcome back. If you've been following these videos in sequence, we've been working on a one sample t-test. We already introduced the equation, then we worked through an actual problem. We found that it was not statistically significant in this particular example. So if you're kind of lost so far at this point, you may want to watch those last couple of videos, maybe the last 3 videos in this playlist to make sure that you're on the same page. Otherwise, if you're just kind of reviewing how to calculate the effect size and confidence interval for a one sample t-test, this will be a nice review, but I'll be using data that we used in a previous example. So that's where I'm getting all of this information. So let's go through. Okay, so the equation for a Cohen's d, which is a measure of effect size for a one sample t-test, is almost exactly the same as the Cohen's d equation for a dependent samples t-test. So we'll take a look here. As you can see, we've got this right here. It looks almost identical. Almost everything's the same mean, same population mean or target value in this particular case. However, it used to be the difference scores, right? The sum of the squares of the different scores and the sum of the different scores. Now we're just taking the single samples information, the sample that we actually collected the information from, okay? And so as you can see here, we've got the mean difference in the numerator, and then down here is the actual standard deviation of the sample that we collected the information from. So we already have all of this, of course, because we had to calculate all of this information using our equation for the t-value in the first place. So we covered all of the math here in the previous couple of videos, but let's take a look at these equations side by side. So as you can see here on the left, this is the equation for Cohen's d, the measure of effect size we're looking at. Over here on the right is the equation for the t-value, the one sample t-value that we already calculated. As you can see here, we're just taking the numerator and moving it over here, but then down here we're taking almost the entire denominator and moving it over here. Of course, in the t equation, this is called the standard error of the mean. The only difference is we're taking away that denominator of dividing by n and just leaving the standard deviation in this case for the d equation. So that's essentially all we're doing. Now if I plug in the values, this is what we come up with. Here you can see the values that we actually had from the original equation. Now I had all of this math in an earlier PowerPoint, an earlier slide. So if you're not sure how to obtain these values, I walk you through an actual data set to how to do that. Naturally, use the data that you're working on for whatever problem you're solving, but if you need a reference point, this is how we came up with all of this. So all of these values were already computed, and in our t equation for a one sample t-test, I'm just moving them all over here to the d equation. So once again, the d equation. Once again, you've got this is the standard deviation here, as long as I'm not dividing by n again, which in this case is 11. So that gives me the standard deviation over here. So of course, now all we do is simplify at this point. We're all done with the t equation, so we're not going to look at that anymore. And we'll start looking at the d equation. Now, of course, the difference between the mean and the target in this case was negative 152.27. In this case, it was dollars. Once again, the scenario was I wanted to compare a sample to the national average in credit card debt. And then down here, of course, is the standard deviation. Before I take the square root, again, you can do all the math from the previous information. So, of course, the square root of 21,447,007 and 22 cents, $7.22 is 4,631.09 cents. And of course, we divide that by that to get negative 0.03. Now, of course, our interpretation at this point, we use the same metrics that we've used for the independent samples t-test, effect size d, and the same thing goes for the dependent samples d. Now we're using the same thing for his. So Cohen's d is always interpreted essentially using the same metrics. Although, once again, the verbiage is just kind of, it's certainly subjective. It's just somebody decided to use these metrics. So if, take them with a grain of salt. But if you're in a beginning statistics class, just use whatever your professor tells you to use. In my class, this is what we use. And this is based on other information that other people have come up with. Anyway, so the point is a negative 0.03 is, of course, a very small effect size. In fact, it's so minuscule that I would say there is no effect. There was no detectable effect of one variable on the other. There was no detectable effect of the independent variable on the dependent variable. Now, however, we knew that anyway just with statistical significance. If you recall in the previous video, I said because it was not statistically significant, or t-value, then there's really not a reason to go on and measure the effect size unless you wanted to be like, well, I knew I had too small of a sample. Let's see what the effect size was. And it might say, oh, the effect size was actually small. I just need a bigger sample to detect the effect then, right? It is possible to have a small effect size, but a not statistically significant t-value. So in any case, what we have here is essentially no effect, right? And what I can do is update my findings because we had a one sample t-value with 10 degrees of freedom. And the actual value of the t was negative 0.12, again, not statistically significant, which is symbolized here. In other words, there's a greater than 5% probability that we're committing a type 1 error if we reject the null hypothesis. Therefore, we're not going to reject the null hypothesis. We're not going to say that there was an effect when when we have no evidence to suggest that there was an effect, right? So we can just kind of summarize that as this. We really didn't find any evidence that the churchgoers in our sample differed in terms of credit card debt from the national average of $6,500 in credit card debt. Okay, so that's that for the effect size. Now, again, the effect size is a measure of the effect or the size of the influence of one variable on the other. And again, we didn't really see any effect whatsoever. So now let's take a look at confidence intervals. So the confidence interval, again, once again, if you have a non-statistically significant t-value, there's not exactly a reason to go ahead and compute the confidence interval because it doesn't really tell you anything different than what your statistical significance told you in terms of, like it's not like you're going to magically find that there was an effect. This just gives us a better idea of just how close we got to a significant mean difference for one thing. So I suppose we could do it just as an exercise, and that's what we're going to do right now. Now we know, of course, that we're going to include the value of 0 in between my confidence intervals, the high and the low, because we knew it was statistically non-significant already, right? We already found that there's a greater than 5% chance of committing a type 1 error if we reject the null hypothesis. And so we already know that it's not going to be statistically significant, but we'll go ahead and run through this so you can see the equation. And then I think it's important to, just as frequently as we interpret significant effects, to interpret non-significant effects as well so that we're familiar with how to do that. So again, very similar to the dependent samples confidence interval, which makes a lot of sense, hopefully. Again, we have 95% confidence interval is equal to the mean of our sample, the mean of the x value, or of course you could call it whatever value you want, but it is the mean of the dependent variable that we were measuring, plus and minus, so we're going to come up with two values, the critical t-value, which we obtained previously in the previous video, you can take a look at that, and here is the standard error of the mean, of course. So it's that same denominator that we had from the t equation. Okay, so we already have all this. We're not going to go through all of the math then. We're just going to pump in the values that we left off with. So we had a numerator or a mean difference, essentially. The mean difference in our numerator was negative 152.27. And the critical t-value, of course, for this kind of test, a test with this many degrees of freedom, I'll say, with these characteristics, is 2.228. Again, that's all in Appendix B, and we've run through that in previous videos. And the denominator in our equation, the standard error of the mean, was 1,396.33. That's everything we need to plug into our equation for the confidence interval. We start with our mean difference, the mean difference between our actual group, our sample, and our target, negative $152.27, plus and minus the critical value, and that, of course, is our standard error of the mean is $1,396.33. Okay, so now let's do the math. We start there with, once again, 95% confidence interval, starting at that point. And the first thing we can do is, of course, multiply that, because we have to multiply before we can add or subtract, right? That's our order of operations. So if we multiply that by that, we get $3,111.02. So we're starting at a difference of $152.27, and then I'm going to add and subtract this many dollars here. Now, I explained this in my very first confidence interval session. I think what makes the most sense here is just to remove the negative sign. It makes more sense in my head. It doesn't actually hurt anything if you like to keep it in there. All it does is switch around which value is going to be the lower value and which value is going to be the higher value, the upper limit and lower limit. The interpretation stays the same, essentially. I just think it makes more sense because you can't have a negative difference, right? That kind of makes you dizzy a little bit. So I always like to just remove the negative sign, but it doesn't actually matter. So we'll go ahead and remove the negative sign for my purposes and then move on. All right, so I've removed that negative sign from in front of the 152.27, right? So my starting point is here. It's positive now. But all this is a difference. It's just giving you an idea of the size of the difference between the mean and the target, and that's fine. Okay, so to get the upper limit, I of course add the difference over here, right? So 152.27 plus 3,111.02 is of course 3,263.29, and that's in dollars again. Now, essentially what I'm saying here is that given the characteristics of my sample and my data set, I can be about 95% confident that the whole church's mean credit card debt, in other words, the population's credit card debt, in this case that's defined as that whole church, their credit card debt is not more than $3,263.29 higher than the national average, right? In other words, I'm saying probably the maximal difference between the group I was targeting and the group that I actually sampled probably isn't any higher than this, right? It may be higher, that's possible, but as long as I did my due diligence in my collection of the sample and it represents the population, this is my best guess. So now you might say to yourself, that's a big difference, and it is, right? That's a pretty good indication that because it's that different, we probably didn't have a statistically significant finding, especially given the scale that we were working with, which is, really not right around 6,500. 3,263 is quite large. Okay, so now let's find the lower limit. Okay, the lower limit, of course, is done in the opposite way. We simply subtract the guy over here that we had from our starting point. And in that case, of course, we get a negative value because this is bigger than that, right? Okay, so we end up with a negative 2,995.75. Now here's where confidence intervals get kind of interesting in that we have a negative number, but what it's essentially saying is that it probably wouldn't have, well, it's essentially right here. We're 95% confident that the entire church's or population's mean credit card debt probably was not more than $2,958,075 lower than the national average is essentially what we're saying. That's why the negative is there. So it's probably not, that's still a lot of debt, but probably not lower than the national average in this case. Whereas in the upper limit, we were saying it's probably not higher than that value compared to the national average, okay? So again, a little difficult to deal with the negatives and positives because it doesn't mean that they're in more debt. It doesn't mean that they're in, I guess I could, the upper limit would mean maybe that they're in more debt. Beyond what the 6,500 was. But again, we're not using as like a starting point of 0 in this case, right? Because we were comparing it to 6,500. And so therefore, this is above or below that national average. And in this case, we're saying probably not $2,958 below 6,500. Okay. So once again, that's a very wide range, negative 2,000, almost 3,000, and upwards of 3,000 positive, of course, includes 0 in there. And so we knew it was statistically non-significant anyway, but that's just one more nail in the coffin, so to speak. So again, what we have here is essentially no effect whatsoever of the difference here. We found no difference whatsoever between our sample in this church and the national average, okay, using that as our criterion. So this is the way that we can summarize this. We had some of this previously, but you can add on all this. So again, we can add in the effect size here, a d of negative 0.03, and of course anybody who's relatively familiar with statistics will see that and go, oh yeah, that's very close to 0. That's essentially no effect whatsoever, no detectable effect. And the 95% confidence interval for the mean difference specifically, right? Because you can have confidence intervals for other things as well. And then you list those here. The lower limit, of course, becomes first, and the upper limit is next. Okay, so once again, we have no evidence to suggest that our sample was any different from the population at large or the national average in this particular case. Okay, that is it for one sample t-test. Now we're all done with t-tests in this series. The next thing we're going to do is try introducing more than 2 means and see if we can compare them simultaneously. That's something called an analysis of variance. So I'll see you then.